So it's a two-part talk on concurrency in C++ language. So it's kind of a very general overview of concurrency features that we have in the language, their evolution with the standard, and I don't want to be basically the audibles for CppReference.com. You can go and read that yourself. So I'll show you not everything, but a lot of things, and I will show you basically what they are, where to find them, what they are for, and then if you want to know more about each individual construct or object or class function, you can go read about it. I'll tell you sort of the types of things that are possible, but more importantly, I'll tell you basically the reasons for them and the kind of lessons that you can learn from the design of these features in the standard for the design of your own software when you build it. So at the same time, I'm not going to be like speaking in standardese. The programmer's perspective basically means what's in it for me as a programmer, and it depends on who you are with regard to this programming. So, and in a lot of ways, it's kind of make your own adventure, because I have never given this talk as a two-part talk, so I added a lot of material, but I also don't want to bore you with something everybody knows. So let's see where you're all at. Who has never written a concurrent program in C++? Okay, so everybody was writing some concurrency. All right. So who has the luxury of starting a new project and is not bound by existing code base? Okay, quite a few people. All right. Who is working on an established system that has concurrency? Okay. And who is writing libraries? More than half of you. All right, so basically, if you were starting your first concurrent program, you get a basic set of tools with a few things missing, which is like almost enough. If you are an experienced programmer starting a new project and you want to use nothing but the standard, you get kind of enough to get you hooked, not enough to actually complete the job. If you're working on an established software system, you probably already have everything you need, so why would you need this at all? And I'll answer that question. For the library, well, it's one of the ways to get all the low-level tools you need. It's not the only way, but it's one of the ways. But more importantly, and that's for everyone, you get guarantees provided by the language. You get a dictionary, you get a vocabulary that you can use to speak to other programmers that is common, enshrined in the standard, so you have certain assurances that you will understand each other. And a kind of a way to think about and to reason about these concurrency problems that, again, is common. So when you discuss your concurrent designs with other people, you have kind of a common starting point. So a lot of the presentation will actually be on those last three items on the slide. And with that, let's start the first part, which is the introduction into the language. I'll show you, in the introduction part, I'll show you like the basic language features, tell you when they appeared, how to use them, what they do. I'll show you a few of them in real life. So let's start with before C++ 11, so C++ 03 and earlier. This is all the standard has to say on the subject of threads. Fits on that one slide. So there is no word thread, there is no word concurrency. Okay, why does it matter? Because in practice, okay, who was writing concurrent programs before 11 rolled in? In C++, I mean, not. Okay, so quite a few people were, so why does it matter? And we'll talk about that specifically. Then C++ 11 came in, introduced the thread both as their type, an object thread, and well, not the object, it's a function, but as a concept. Memory model, which will differ for a little bit, a bunch of concurrency primitives, promises and futures, atomic operations, memory barriers, which relates to memory model, thread local data, thread safety guarantees. We'll cover all of those. C++ 14 added a couple primitives, synchronization primitives to the standard. 17 added a few more, and the big thing was parallel STL. We will cover that in the second half. 20 added a few enhancements here and there to existing classes, and the big one was coroutines. And I'm talking specifically about concurrency additions, of course, concepts and stuff, but that's kind of orthogonal to concurrency. So I'm only focusing on the concurrency-related additions. OK, let's start with C++ 11. And go ahead and ask questions. In order to understand the importance of what they did in C++ 11, because it's more important than they added, gave us a couple headers. It's a lot more than that. Couple headers are really not that big of a deal. In order to answer that question, we have to understand what didn't we have really, like what was really missing before that. All right, so this is how you wrote code in C++ 03 for concurrency. It looked something like this. Yeah, you might have had a class that encapsulated it, but I'm stripping off that class, and that's what it boils down to. So if we have some computation that needs to be logged, we called, let's say if you were on a POSIX system, we called the pthread functions. If you were on Windows, you called the Win32 API. And this is how you wrote the code. Now, let's look at it the way a C++ compiler looks at it. We only know C++ standard from this point forward. We don't know anything else. We clearly notice that the pthread mutex lock operates only on mutex. Let's assume that somehow the compiler either knows that X is not global, or it can see implementation of pthread mutex locks and it knows that X is not involved anywhere in that implementation. Let's assume that compiler can deduce that there is no aliasing, that really pthread mutex locks operates only on mutex. And the same for unlock. The middle line clearly does not depend on mutex. Again, if we can prove that there is no aliasing of any kind, it doesn't depend on mutex. Well, one of the most common optimizations that the compilers do is hoisting the common sub-expressions out of the loop. This is what it looks like in this case. According to the C++ standard, this is a legitimate optimization. Well, it would be whether or not it has to repeat it 10 times. Maybe it has to, maybe it doesn't, depending on what it knows about the functions. That's not important. Either way, you really don't want the compiler to do this. Everybody understands why you don't want the compiler to do this, yes? OK. On the other hand, nothing in C++ 03 prevents the compiler from doing this. So in practice, like everybody wrote the code like this, so it worked. Why did it work? And the reason it worked is, well, OK, before we start the reason it worked, here is another thing that you do. You have an array of ints. And on one thread, you do some operations on this data sub 0 element. And you assign some value into it. And on another thread, you do some operations on data sub 1, and you assign another value into it. Is that thread safe? Again, the standard says nothing about thread safe because it doesn't even have that word in. But whatever guarantee does that the previous example work, there is some magical thing in practice. There is some magical thing that guarantees us that the previous example with locks worked. Does that magical thing still guarantees us that this works? OK, who thinks, out of the people who programmed before 11 for concurrency, who thinks that this, in practice, was thread safe? Who think that that wasn't thread safe? Maybe. OK, What if instead of int we have some type t, which is not int? Did that work? Depends on the type t. All right. So now let's actually find out what the magic is. The magic was that every compiler that was allowing you to write concurrent programs in practice took upon itself to obey another standard. And in case of pthread mutex locks, it would be the POSIX standard. So, for example, GCC was constrained by two standards, not one. One was C++ standard, and the other one was POSIX standard. And the POSIX standard, among other things, those names, pthread, mutex, lock, and so on, they were actually mentioned in the standard as things that you shouldn't move around. Basically, they, that it has a global side effect. You should not move code across these invocation calls. Now, there were still few problems with that. One, none of these standards were actually as portable as C++ itself was. On Windows, you had a Win32, which also has its own standard for the concurrency calls, but not necessarily the same as POSIX. Two, for example, POSIX actually does not tell you what this does for all types T. And in practice, if you were on x86, this was thread safe if it was aligned correctly. And if you change it to bool, then it wasn't. And if you change it to short, then it may or may not be, depending on the code gen, or on what code compiler actually generates. But with bool, it was very easy to observe that this races, that this gives unpredictable results. Because POSIX actually did not specify that as part of its standard restrictions, that accessing adjacent elements of a bool or char array should do anything, is restricted in any way. So what was missing? The thing that was missing, that magic thing, is called the memory model. And that's why we have an entire part of this talk dedicated to memory model, because that's what we got in C++11. We had a POSIX memory model, which doesn't, as it turns out, it does not provide sufficient guarantees for writing concurrent programs. We had, I don't know if Win32 provides sufficient guarantees or not, but in any case, they would be different from POSIX guarantees. And anybody tried to cancel a thread like before C++03, like in POSIX? If you did, you would find out that the different versions of POSIX standards stated slightly different things about what should happen if you do. All right, so I'm going to defer the discussion of the memory model because I don't want to go into kind of semi-philosophical discussion right away. I want to show you a few concrete things first. So C++11 came in and gave us the memory model, which I'll show you. But it also gave us some practical tools. So let's see the practical tools. First of all, we got the thread. The way they implemented the thread is like this. It's basically a type erased thing. So you give it a function pointer, you give it the arguments, and it's an object. The constructor is a template. The object itself is not a template, so there is type erasure going on inside. When the object is created, this callable is invoked with these arguments, creates a separate thread, runs. In C++11, you have to join it yourself. If you destroy it without joining, it's undefined behavior. Any callable returning void is allowed. You can use lambdas. So, as I said, it's type erased because the object itself is not the template. The constructor is. Inside, it's probably done with runtime polymorphism, like a normal type erasure. A lot of libraries before C++11 were making threads like visible classes you would derive from a common base. So the class itself was a template derived from a common base. Doesn't really matter. I mean, they chose this way it's equivalent. There is no way to reuse this object. After the computation ran to its end, you have to delete it. Well, okay, let's see how it works in practice. Okay, so C++20 did one minor addition. It stuck the J in here. And all it does is it calls join in the destructor. That's it. It's the exact same thing, except destructor automatically calls join. Simplifies a lot of coding. Basically, you don't have to manually. If you destroy the plain thread without J, and you don't call join, it's UB, and actually, like on GCC, it will terminate. All right, let's see what it does. Well, okay, let's see what the code looks like. So ignore the log guard stuff for a moment. I have so this is my thread. It'll start a new thread, and it'll keep printing the asterisks in a loop. And this is the main program, which will create a thread, and then the program itself will keep printing dots in a loop. So here they're both running at the same time, and they're printing interleaved. Their print statements are interleaved. They're on different sleep schedules, so the two beats are not commensurate. That's beating at 3 and 5. That's just how long I choose to sleep for. That's just to show you that they're running at the same time. Okay, so it creates this thread and calls a function on it. Now, what do you use this for? Okay, let's see. Lots of different users. So let's see who use threads for pure performance, just to get more computation done. Okay, that's all everybody. What about asynchronous operations that aren't particularly intensive in computing? You just don't want to wait for them. Okay. No, if you do it in an HPC context, you want to use more hardware resources. You have multiple cores, you want to get more out of hardware. If you're doing, for example, a UI, you just don't want the UI to freeze while it's if your program needs to do like half a second of computation, you don't want UI to freeze on you. Sure. Or if you're waiting on a socket, you don't want your main program to block while you're waiting on a socket. So you task a thread with waiting on a socket. It doesn't actually use any CPU. So you're not utilizing any more CPU. Your main program still like one thread running on that CPU. You just don't want to block waiting on a socket. So the second thread doesn't burn any CPU. That just asynchronously waits on a socket, so your main program doesn't block. Things like that. Okay, so why isn't this enough? I mean, C++11 gave us threads. Seems like, okay, we're done. You have a lot of parallel computing to do. You create a thread, put the computation onto the thread, join the thread when you want the result. You join the thread. Join will block if the function is still running. It will not block if the function is already done. Whenever the join actually completed, you guaranteed that the function completed. So whatever the result it produced, they're finished. These are threads, so it runs in the shared memory. You have access to the same addresses. So if the thread writes into some variable, that's how you get the results out. So then you can look at the data. So we're done. Well, not quite. And I have to explain to you now about what are the threads and what is the nature of the threads. So the threads, first of all, there are two kinds of threads. Well, at least two, but we're talking about two. There are kernel threads, which are independent instruction sequences from the point of view of the processor. Well, and the OS, obviously, that manages them. So operating system schedules kernel threads to run on the CPU. You can have more kernel threads than you have CPUs, but at any given time, one CPU will be executing instruction sequence from one kernel thread. Now, if you have SMT, then it's effectively like one CPU is effectively two CPUs. So then I would say these two virtual CPUs can execute instruction stream from two threads. But for the purposes of this talk, I'll just treat SMT cores as two separate cores. SMT is just stands for symmetric multithreading. That's what Intel calls hyperthreading. All it does is basically it's really one core with a little bit of extra hardware that allows it to have another program counter. Okay.
Isn't it hyperthreading on Intel and SMT on AMD?
No, SMT is a general term. SMT was actually there before hyperthreading. And like even on like on some of the Intel machines in the BIOS, that option is enable SMT. Any other questions? So SMT is not going to be important for the purpose of this. So the CPU info says that I have 16 CPUs on this machine. That's with SMT enabled. I'm going to pretend that I have 16 CPUs on this machine for the duration of this talk. Okay. Now, at any time, as I said, one of these kernel threads run on every processing core. The kernel is in charge of deciding which one. When you create a new thread in the user space, what you get is a user thread. The operating system runs all the user threads on all the kernel threads, or however many kernel threads it wants to use for running your user threads. Now, if you worked on Linux or on Windows, you're probably used to not having that distinction. And that's because both of those operating systems support what's called one-to-one threading model. One user thread is mapped to one kernel thread. Okay, anybody has worked on a system that had a different one, that had more user threads than kernel threads? No? Solaris? Anyone? AIX? Okay, so there are operating systems that have what's called M2M model, where you can have n user threads that are mapped to m kernel threads. From the user point of view, there are n independent instruction sequences. From the processor's point of view, there are m independent instruction sequences. The OS maps your user streams to kernel streams and decides basically. You can think of it as user threads are tasks that are running on a thread pool that kernel threads form that thread pool. So this is kind of the easy mental model for this. Now, std thread creates a user thread. No OS that I know of can manage a huge number of kernel threads. And by huge, I mean like millions. Because what would happen if you said that I'm going to take all my independent computations, I'm going to create a thread for each one, and just let it go and wait on it all at the end? Well, in a program with a lot of intrinsic parallelism, you would be able to fire off millions or maybe even more of independent tasks as std threads, and then on a one-to-one operating system, it would go ahead and create millions of kernel threads. I'm not going to demonstrate this because I would probably have to remove the battery from this laptop to recover to force it to reboot if I did that. So in reality, you almost always get one-to-one model. Your second option is to get a very badly broken end-to-end model. There is, lore of secret knowledge of how to write a functioning end-to-end model. I think in this room, I think only one person have actually seen it, and that would be you.
I worked on ASMT
Solaris didn't have, Solaris had the broken one. AIX was the only one that I know that actually had a beautifully working end-to-end threading model. You could actually go ahead and create 10 million threads, and it managed it for you.
How did it manage the stack space?
Well, you could run out of stack space. You would have to reduce your. I mean, presumably, if you're calling that many functions, at the same time, each one doesn't have that much stack space. You would have to reduce the stack space. So it's just like on Linux, it's configurable. But the important part is it wouldn't try to actually run all of them at the same time. It basically ran a thread pool under covers, treated your threads as tasks, and executed. Well, the second reason why you don't want to do threads directly is threads are actually very expensive to start and join. At this point, you should demand that I prove it to you, because never take any statements about performance on faith. Performance should always be measured. Now, I am going to prove it to you. So, let's see. I'm just going to do it repeatedly to average the results, but this is what I'm doing. And this time I'm actually doing it with a C++11 thread. So I'm starting a thread. Within the thread, the first thing and the only thing I do is I'll capture the clock. Before starting the thread, I'll also capture the clock. And when I join the thread, I'll also capture the clock. And that's all I'm doing. So this will tell me, basically, after I ask it to start the thread, how quickly the thread actually can begin doing useful work. And also how long it takes me to join. Number of threads. Okay, I can do 8 on this machine without overloading, and I could do 16. So as you can see, the average time to start a thread is 0.1 millisecond. To join the thread twice as much. The worst case, in this case, it's about the same. Okay, 16 threads. This is actually a pretty long time for computation. Like individual operations are measured in nanoseconds. Microseconds are typically like hundreds of thousands of instructions you can execute in this time. So this is a lot, which means you actually can't put short computations into these threads, because you would take longer firing up the thread than doing the work. So if your computation takes less time than this, you're better off doing the computation on the main than firing the thread for it. Okay, we just measured it. There are several things you could measure. You could measure the throughput, which is how many threads you could launch per second, the latency, the delay. But the bottom line is, all of these delays are significant compared to the computation times. Tricky to measure, as I said, but we get the idea. So how do we use the threads correctly then? Since threads are expensive to start and join, we have to start a small number of threads. You can start 1 per CPU, maybe you can manage 2 per CPU, but not a lot more than that. And then you have to manage your own work on those threads. So you keep those threads alive for a long time, so you don't pay the overhead for starting and joining them. And you get those threads to execute the pieces of work, they're usually called tasks, that you have. And when it's done executing the piece of work, you don't join the thread. You tell it to go find another piece of work to execute, and so on. Now, this is at least true for computational threads, for HPC threads. The background threads, like waiting on sockets, that's a lot easier, because OS actually manages large number of idle threads reasonably well. Probably still not millions, but like 10 times more than CPUs, no problem. If the threads are just sleeping, they're much easier to manage for the OS. So if you have, so for example, in our distributed software system, we can be talking to, we talk through sockets to every remote machine, and we can run on 20,000 of those. So and we use one thread per socket. So we would fire up 20,000 threads just to manage the sockets, no problem. They're mostly asleep. They wake up when there is something to do with the socket. So background threads are easier. Computing threads, you want to manage them yourself. All right, what tools do you have for that? I'll briefly mention it, and the reason I'll briefly mention it, because I'm only mentioning to tell you what not to use. And I'm not going to demonstrate that either, because the end result will be either it won't scale at all, or it'll kill the machine. There is the async, there is a future, there is a promise. Now, future and promise are just the types. Future is a placeholder for a result that will be computed asynchronously and will materialize sometime later. Promise is where the thread that computes the result that will be computed sometime later puts it temporarily until the promise becomes the future. These are just some types. By themselves, they don't do you any good. Async is the thing that actually executes that action asynchronously, or whatever computation you want. In theory, that's all you need. In practice, if you want a background thread, that's not so bad. On the other hand, you might just launch a background thread. It's not that hard. If you want to do computations, you don't. For performance, this async stuff is entirely useless. The standard actually doesn't say that thou shall implement this as badly as you can. But in practice, that's what everybody does. The usual implementation, so the standard gives you two options when you launch it. One is asynchronously, one is serially. If you ask it serially, you get no scaling at all. These async tasks are actually executed, like as you call them, they get executed one time. If you ask asynchronously, it immediately fires up in practice. It's not required to do that, but every implementation that I've seen immediately fires up a bunch of threads. And now we're back to running 1 million threads all at once and choking up the machine. So what we really need is a thread scheduler, and we haven't got that. In C++ dialog, the thread scheduler is called executor, and we haven't got that yet. All right, std future and std promise, they are just types with some convenient member functions. If you have your own thread scheduler and you like them, feel free to use them. Almost every library that actually implements a thread scheduler has their own version of futures and promises that is part of the library, and sometimes they look a lot like standard C++ ones, and sometimes they don't. Either way, no big deal. All right. Well, if you have threads, you must have locks. Everybody who programs with threads has locks. So any questions on threads, by the way? No? OK. Locks. C++ 11 gave us that basic mutex, std mutex. Has lock, unlock, try lock. It's actually implemented, it just forwards all of its calls to the operating system mutex, POSIX mutex on Linux. The way you use mutex is like this. Before doing some unsafe computation, and I'm dropping a lot of words that I haven't defined yet, like unsafe computation. I wanted to show you the toys, and then we'll talk about memory model, because it's kind of drier stuff than this. So you lock your mutex before doing unsafe computation, and unsafe computation is the one where you are competing for the same output from multiple threads. So I'm adding to the sum on multiple threads. This is unsafe. Well, actually, never write code like this. So no, do not use mutex like this. The way you use mutex is like that. And the reason is the same as with any resources. If you throw a return out of here, this is left locked permanently. There is nobody to unlock it. Nobody else outside knows that they might be responsible for unlocking it, which means it's locked permanently. The next time you try to lock it, you'll deadlock. So no, do not use mutex like this. Right away in the same C++ 11, they gave us this, which is just a resource acquisition type wrapper around the normal mutex. The constructor locks, the destructor unlocks. This is a C++ 17 syntax. I'm deducing the template argument in the constructor. In C++ 11, you would have to put the mutex type in here. It basically provides you provides you automatic unlock. It makes it exception safe. There is a slightly more complex thing called unique lock, which can do that, but it can also take ownership of a locked mutex and transfer it. It's kind of like unique pointer for locks. If you just destroy the unique pointer, you destroy the object. You can move out of unique pointer. Now you have another unique pointer somewhere that now owns that object. Same here. Unique lock is the same way. If you move out of unique lock into another unique lock, that one now owns the resource. Now, there are a few more mutexes. So doing this on one thread, as written here, is a guaranteed deadlock. Why? Well, this thread is holding the lock. This same thread is trying to get the lock. The second call will block until somebody unlocks the lock. The only thread that can unlock the lock is the one that's holding it. Trying to unlock a lock from another thread is actually undefined behavior. But this thread is not making any progress. Wherever the call to unlock is, we're not getting there because we're blocked here, which means this is a guaranteed deadlock. It's best not to do that. If you really have to do that, and pretty much the only place where you end up maybe having to do that is if you have classes with internal locking. Like, so let's say you want to create a safe vector, and you put an internal mutex into the vector. And now one method locks and does its stuff, but then it calls another method for something. And that other method is also public, so it also locks. Now you've done that. Well, it's better not to do that. It's better to create alternative private non-locking versions of your methods and call those. But if for some reason you have to do this, there is a recursive mutex that reference counts. Another interesting thing that they gave us in recognition of the problems with mutex. Here is one thread. We have some mutexes. Here is one thread. Locks M1, then locks M2. Here is another thread. Locks M2 first. OK. Then locks M1. The problem is that this thread is already locked M1. That thread locked M2 successfully. Now thread 2 tries to lock M1. No can do. Thread 1 tries to lock M2. No can do. Both of them are responsible for unlocking the mutex that they already lock. But they can't get there because they're both waiting on some other mutex. Again, that's a guaranteed deadlock. What they gave us is this function std_lock, which whatever algorithm it uses internally guarantees that no deadlock will happen. In C++ 17, we got this thing called scoped lock, which, so notice that this is a function. This is not an object, this is a function, which means you call this to get the locks, and then somewhere down there in your code, you have to call unlock on all of them. The order there doesn't matter. You can unlock in any order. It's the locking that kills you. But now we're back to throwing exceptions before unlocking the locks. So you used unique lock in conjunction with std_lock, because unique lock will can own multiple locks, will call lock on them, and well, you can call lock on them yourself, and then unique lock will unlock the mutexes. In 17, you got the scoped lock whose constructor takes multiple mutexes. So internally, it does the same thing as lock does, but it does it all in one shot. The destructor unlocks all the mutexes. In C++ 17, we got shared mutex, which everybody else calls read-write lock. Now, in C++ 14, we actually had shared timed mutex. I have no idea why we got timed mutex before the non-timed one. Maybe somebody knows on the standard. Here, I'm sure somebody knows. Maybe somebody here knows. You can do the plain lock gives you exclusive or write access. If you hold exclusive access to a mutex, nobody else can get any access. Everybody else will block. If you only hold shared access or read access, Somebody else, another thread, can also get shared access, but an attempt to get exclusive access will block for them now until everybody releases their read access. So read-write lock. Very cool idea. In theory, performance usually is pretty bad. There is a object-oriented the object wrapper for it against the shared lock in C++14. We got conditions and condition variables, which are modeled really, really closely on pthread condition. And in fact, on the POSIX system, they call pthread condition. You have a pair, condition variable and a mutex. The protocol is between two threads. So you lock the mutex. So let's say, so this is how you transfer data from one thread to the other. Producer locks the mutex, constructs the data that is guarded by the mutex, notifies the condition. This is in pthread language, that's called signaling condition. It has nothing to do with signals. Signaling the condition has nothing to do with like signals in Unix sense. On the consumer thread, so unique lock acquires the ownership of the lock and tries to lock it. And then you wait on the condition. The condition actually does two things. This wait does two things. You have to give it the lock. And internally, it unlocks the mutex. And then it waits on the condition. So this blocks, but not on the mutex. And the reason is you want to give up the ownership of this mutex so the producer can actually produce the data for you. Producer will then come in, lock the mutex, because this mutex guards our data. So producer will come in, log the mutex, will do stuff to data, safe, knowing that we have exclusive access to the data. Because if we say that mutex guards the data, it means that everybody else who would like to do something to the data must acquire the mutex first, but producer already locked it. The producer will then will unlock the mutex, so the closing curly brace unlocks the mutex. Nothing happened here because this wasn't locked on the mutex. This was blocked on the condition, not locked, blocked on the condition. We notify, and now the consumer thread wakes up, relocks the mutex automatically. This is all done inside the wait call. Relocks the mutex. If somebody else managed to lock the mutex in the interim, that attempt to relock will block until you can actually succeed to do that. Once you finally relock the mutex, you come out and you can consume the data. So that's a condition-based handoff protocol. POSIX people were doing that like since, I don't know, 70s, wherever POSIX was introduced.
Is there any reason you didn't use the unique lock on the producer side?
In this case, they're exactly equivalent. Yeah. And that's basically what I wanted to show. That for the simple use like that, they're exactly equivalent. Yeah?
But on the consumer side, you must use unique lock to be able to unlock it.
On the consumer side, you must use something that you can pass in here. Yes, so you can't pass lock guard here because unique lock has lock unlock. It exports. So unique lock behaves like a mutex. It exports the unique lock itself is a lock, so you can actually put a lock guard on a unique lock. Not that you would want to, but syntactically you can. Unique lock behaves. Yeah. So thank you. I forgot to mention it. Unique lock behaves syntactically like a lock. It has lock unlock, so you can pass it into anything that into which you can pass a mutex. And this requires you could in theory pass a mutex into this. You would just be naked mutex. You would just be responsible for unlocking it later. That's all. Here you can use unique mutex if you want. Sorry, unique lock, or you can use lock guard. Yeah.
I believe the distinction is lock guard is literally just a constructor and destructor.
Yes. So the question was, lock guard is just a constructor destructor. That's absolutely true. Unique lock does a lot more than lock guard. In particular, it exports the lock the mutex interface, and it has a move constructor. You can transfer ownership or move assignment operator. But if you don't do anything else to it, if you just construct it and let it go out of scope, it does exactly the same as the lock guard. one other thing with unique lock, you can construct it without actually locking the mutex. There is another argument to the constructor that you can give that tells it to defer locking the mutex. So it takes ownership of the mutex but doesn't lock it. Until then you have to call lock on the unique lock itself, and then the destructor will still unlock. So unique lock can do more things. Also, if you're using, so this is C++11 so far the same, but in C++14 because you got shared mutex and shared lock, now you can use both unique lock and shared lock with a shared mutex, and then they will take their, so unique lock will take the unique exclusive access, the write access, and the shared lock will take read access on the shared mutex. The names are match. There is basically everything that I have shown you, there is a timed version of it. And what the timed version does is you give it an interval, it tries to lock for that much time, or less. It could give up spuriously, but ignoring that, that's how long it will wait. If it couldn't get the lock, or the condition wasn't signaled so it couldn't get notified, it will give up, return, and let you know that it actually didn't get the lock. So if you basically have something that's like using timeout, you want, if you couldn't get the lock quickly enough, you want to do something else for a while and then try to get the lock again, you have these timed versions. All right, a few more interesting things you got in C++11, which aren't part of any header. One is local static variables. The standard always says that these are initialized as the first use. What's the first use? In C++03, the first use is the first use, the first time you call this function. There's nothing else. Because nothing happens at the same time as something else. There's no such concept. In C++11 there is. What if I call this function at the same time on two threads? Which one is the first use and what happens to the other one? We'll talk about this in a lot more details when we talk about memory model, but C++11 says this is guaranteed to be thread safe, which means exactly one initialization happens exactly once, and all the threads that didn't get to do the initialization will see the initialized version of it. Barring bugs in some old compilers, and as far as I know, none of the modern compilers have any bugs on this. When it was first introduced, several compilers got it wrong. Std call once is basically the same thing, only it's a function that gets called once. You can always write your own called once by writing a function that returns something that you bind to a static. Now, the only interesting thing is inside this call once, or inside that constructor, if the exception is thrown, then the once didn't happen. So the first successful pass through that code is the one that actually gets to initialize. Okay, here is one that is also not a new function or a new object, but a new storage type. So we have static, we have dynamic, we have now thread local. This is how it's written. Thread local, just basically it goes anywhere where static goes. Well, on the variables, not on the functions. Static on the functions means something else. It's a lifetime thing. It's like static, except there is one. Static, you have one per process. Thread local, you have one per thread. Whenever you start a new thread, new instance of this is created. This is actually kind of interesting to see. Okay, so I have a class that prints when it's constructed and destructed, including which thread is constructing and destructing it. And I'm also printing, so I have this, I have a thread local instance of it at the file scope in this case. I also, inside the function, I have thread local of So this is like local static, except one per. You can do it in both at the file scope and at the function scope. I told you it's just a static. So both of these could be static, and then there would be one per process. If they are thread local, exact same thing, except there is one per thread. You'll see in a moment. I'll prove to you that that's really true. But there will be one of these per thread. They're initialized whenever each thread goes through this code the first time. And on different threads, they're different. So now I'll start a thread right here. Capture by reference so I can actually get access to that. And in here, I'll call function f. And function f will return the address of this. Now, this is not returning an address to a temporary, because this, within a one thread, it's like static. So returning an address of it is fine. All right. So both S and and F are thread local. So on the main thread, so this is my main thread. This is the thread ID. Sorry, the first print. This is my main thread. This is the next thing is the thread ID, and the next is the value of the f of I, right here, the last one. So main thread, thread ID is some large integer number, and that's the last one is the address of the thread. Worker thread, thread ID, different ID, and the last one is the address of the variable I on that thread. So you see, address of I is different on different threads. So they got different copy, different instance of that object. That's what thread local is. Static, but per thread. Within that thread, there is only one. Every time you take address of that static thread local variable, you get the same address on that thread. On another thread, you get another address. Okay, in the interest of time, I'm not going to show you the performance. I'll just tell you that, and yeah, you shouldn't believe me, but come in the break, I'll prove it to you. They behave performance-wise, accessing them is exactly the same as accessing static variables in a single thread. What's the big deal? Why would you use that? Well, the reason you would use that is you can access them without any locks at all, because you have a guarantee that two different threads using the same name, I, are actually not referring to the same object. So you never need locks to access these. So now, of course, it also means that every thread writing into it actually writes in some other place. So at the end of the day, you would have to ask each thread to take its, the result out of the thread local and put it into some shared state under lock. But that's at the end of the day. That's hopefully only once. All the computations you can do on these. So if you have a need for static variables in a multi-threaded program, you can make those static variables thread local. Now you don't need to synchronize them. You can access them the same way you access them in a single-threaded program. So in a single-threaded program, they were static. In a multi-threaded program, you change them to thread local. The only thing you have to remember is you have to ask each thread to put that result into some shared place. There is actually another way to implement thread local that they didn't use, where you can iterate over, if you implemented the other way, you would be able to iterate over all instances of thread local. So in our internal library that I wrote, thread local is done that way. The main thread can loop over all instances of thread local. Of course, that's not thread safe, so you better make sure that all the other threads are halted at this point. But the main thread can go and collect the results without asking anybody to do it. That's not the way they have chosen to do it. Okay, so we've just talked about that. Nothing in particular interesting in C++ 14. A few cool things were added in 20. Synchronization primitives. So we have mutex and conditions, and then they added 3 new synchronization primitives. First one is a latch. And latch is used to synchronize thread arrival. You declare a latch and the count. Every thread arriving to this latch, and by arriving I mean you call that member function, arrive and wait, will block until that many threads, whatever you put in the constructor, arrive, at which point they all unlock. So if you wanted all threads to pause and wait and then run at the same time into some shared block of code, that's how you do it. After it happens, you have to throw that latch away. You can't reuse it again. There's no way to initialize this object and arrive to it again. There is a barrier, different type, stud barrier, which is basically a reusable latch. Or latch is a single-use barrier if you prefer. Barrier you can reinitialize. So basically, barrier works the exact same way. I'll show you the code. So barrier works exact same way. You tell it how many threads you want to suspend on this, and as soon as 2 threads arrive to the barrier, here is my arrive and wait. So the first thread will block. The second thread, because I said 2, will proceed and unblock the first thread. Then they just print stuff, in my case. But you can reuse it. You reset it and then you can reuse it. That's in the main. Okay, I'm not going to run it, but it just holds 2 threads until they both arrive. Useful. I mean, it's pretty trivial, but it's useful. So, by the way, I said that you can reset the barrier. It actually resets itself. So when that synchronization moment happens, so you said barrier of 2. When 2 threads arrive, at that moment, latch just becomes unusable. Barrier automatically resets itself back to 2, and if you start doing arrive and wait on it again, it's again 2. There is another member function that lets you change the count, but if you don't do it, it just as soon as the threads pass the barrier, it just resets itself back to its original freshly constructed state. Semaphores. That's a little different. So it's basically the POSIX semaphore, but we haven't got that one for a while. So that's done it's to hold multiple threads for a certain number of events. So here's how it works. You construct the semaphore in this particular semaphore, you have to give it max count as a type. There is a default for that, which is implementation specific. Now, it has 2 members. Well, it has more than 2, but the 2 interesting ones: acquire and release. When you acquire a semaphore, you will be blocked. When somebody else releases the semaphore, one of the threads that acquired the semaphore will be arbitrarily chosen, will unblock and be allowed to proceed. The remaining ones will still be blocked. And this is basically done usually done to manage resource transfer between threads. So a classic example is shared queue. I have a queue, and there are some producer threads and some consumer threads. The consumer threads come to the semaphore call acquire and block. The producer thread puts in a resource on the queue, calls release once, signaling that one resource became available. One of the consumers will wake up, successfully exit out of the acquire call, and proceed forward with the guarantee that there is one resource that can be taken. Now, yeah, you still have to lock the queue, obviously, to prevent shared access with a producer who may be modifying the queue at the same time. But you have a guarantee that one resource has been placed and nobody has taken it before you. If you call produce twice, release twice, 2 threads will be woken up. Each has a guarantee that there is enough resources for them. Even if the other thread comes in first, there will still be at least 1 left. So this is what the semaphores are for.
I thought the semaphore was to sort of contain the max number, or am I mixing it up?
What do you mean?
You give it a count at the start, right?
The constructor takes it, and then you're arguing.
Yeah, the constructor takes a count Like normally it's a 0, but you can the count. See, the count for the constructor is different from the count for the latch. The count for the latch or barrier is how many, basically how many hits it'll take before it'll break. Here it's how many initial free acquires.
You count up to the number you constructed, and then anything after that.
So yeah, the count of the semaphore gives you. That's why it's very often 0. It's basically you precede it with certain number of resources. So if you say semaphore of 8, it means that there are 8 resources already there, free for the taking. So 8 acquires will succeed before it'll start blocking.
I thought I heard you say that if you set it with 0.
Normally you set it with 0, which means
Release it does so the internal plus 1.
Yeah. Normally you set it with 0, meaning you didn't seed it with any resources, because usually the one who constructs it doesn't have any resources to give. There are cases where you seed it with some number, but like in case of the queue, you have producers which will produce, but they haven't run yet. And like the main thread which constructed doesn't have any resources to put in the queue. The producers will read them or compute them when they're ready. So you create it with 0, which means there are no resources to take. The very first acquire will block because there are no resources there. And then when somebody calls release, it'll bump the count. Yeah, so if you call release and nobody is waiting, it'll just bump the count. And so yeah, it basically, it literally counts how many times you can take stuff out of it, and the constructor allows you to pre-fill it. And the max count, yeah.
Just that the other example that is useful to explain is like the make job server. That you start with like 16 slots, and then each job like gets one of the same, acquires one, and then they release when they finish, which allows other one to pick up.
Okay, so here is an example where you have pre-existing resources. So you start with a certain number of slots. Then yes, a valid example. You start with a certain number of slots to put something, jobs, resources, whatever. If somebody comes in and says, I'm producing another resource, give me a slot to put it in. Well, I don't have one, so you have to increase the number of slots. But you start with 16 pre-made, let's say. Then you put 16 on the constructor. Okay, so we have seen all these tools. We haven't seen coroutines. We haven't seen basically any equivalent of thread pool. I mean, this looks really pretty underwhelming for anybody who did his own work in any existing concurrent system, because, as I said in the beginning, you really have your own already. So what's the big deal?
Just one small comment on TBB.
We'll get to TBB, so hold your comment on TBB, please, because it'll be in the second half after the break when TBB comes in when we talk about parallel STL. Until that point, it's just a cool library, third-party library, which has nothing to do with C++. It'll become something to do with C++ in about, 45 minutes. Before we move on to the kind of philosophical part of the memory model, any questions on the shiny things? No? Oh, yeah, go ahead.
Do all of those have try versions? Like the Semaphore?
Yes, the Semaphore in particular has the try version. I don't remember if it has time try, but you have to go look. So as I said, I'm not going to read you the entire man page for this.
Latch and barrier do not.
Okay, thank you. So the comment was that Latch and barrier do not have a time try. I think Semaphore does. But my goal for this was to tell you these things exist. If you want to use them, read the full documentation. They actually have a lot more member functions. For example, you can arrive to a latch and not wait. You can just say arrive, bump the count, and proceed without blocking. That's you're incrementing the count for somebody else, but you're not blocking. So there is a function like that. There is another function that is wait without counting. So if you set it with a count of 2, and you have 2 special threads that must arrive, and 20, less special threads that must block until those 2 special ones arrive, the 20 less special ones just wait on it, and they'll be blocked forever. They don't count until the 2 special ones arrive, bump the count twice, and now everybody can go through. So yeah, they have a bigger interface that I have shown you. Any other question? Yeah.
I don't remember. Did we ever protect against accidentally not naming the lock guard? Like if you leave out mine here, then you get lock guard goes away at the semicolon, right?
It goes away at the end of the scope, right?
If you don't leave out the word mine.
Oh.
If you don't name it, there's an accident waiting to happen.
Yeah, it will.
Did we ever protect against that?
I don't know. We can. Let's try during the break. We'll try to compile it and see what happens. I want to get through the memory model. Yeah. So basically, this serializes your questions. Okay. If there are no more questions to serialize, let's go do the memory model. And I don't know if they've done that, and in the break we were going to find out. All right, so the rest of the talk, the remaining 20 minutes, I'll be explaining to you basically what's the really big deal about all of this. Because, thread, mutex, sure, but in reality, everybody who programmed with threads before C++11 had that stuff. Yeah, it's a little more portable now. Still, if you had to program for both Windows and Linux, you had the wrappers for this. So what's the big deal? The big deal begins really now. That wasn't the big deal. This is the big deal. What's the memory model and why it's a big deal? Let's start with the definition. There are several differently worded definitions floating around. They all boil down to this. Memory model describes interactions of threads through memory. And a thread, for the purposes of this definition, is a sequence of instructions that can be executed independently of other threads. Why? So interaction of threads, that part is kind of clear. Why through memory? Because they basically don't have any other sort of explicit interaction. They all pretend that they have their own CPU, and really they do kind of. They're running exclusively on the CPU. They can share I/O, sure, but that's still done through memory, at least through the address space. So the memory model describes interaction of threads through memory. Another way to say it is the memory model describes the state of the memory and the guarantees and requirements on the state of the memory that can be observed by multiple threads at the same time. In particular, the interesting part is what guarantees do we have when multiple threads are accessing memory? Now, who is responsible for providing us with the memory model? Actually, quite a few things. First of all, your hardware has a memory model. Now, the hardware always has a memory model. It may be not documented, but it has one. The operating system may impose additional memory model on top of what the hardware does. If you're executing under VM, that machine provides you some kind of memory model. Compiler basically either relaxes some guarantees or adds some guarantees that effectively translate into the memory model for the C++ virtual machine in our case. And all of this together forms the actual memory model for your current program running on a current hardware compiled with a current compiler. That compiler portion came in C++11. Before C++11, we didn't have a memory model in the language, which means the compiler wasn't on the list, which means whatever OS and hardware gives you, that's what you got. Now, we have additional guarantees from the compiler, which are true no matter what these two other ones do. The memory model can never be more relaxed, like looser. And for now, intuitively, I mean, if you have restrictions and requirements, you can tighten them and loosen them. I'll show you what they are, but intuitively you can say if I have restrictions and requirements, I can be stricter about it or less strict. So when you have multiple pieces influencing the memory model, you can never make it looser. You can make it more strict. You can impose more restrictions. But so if the compiler has certain guarantees, it has to do so in such a way that no OS and no hardware can relax them. Compiler may be unable to loosen any of these guarantees that are already provided by the OS and hardware. But it has to force the OS and hardware to not relax the guarantees provided by the compiler. That's how they combine together. So important parts of the C++ memory model. Let's start with the one that POSIX actually didn't tell us anything about. every variable or object, distinct object has a distinct address. Accessing two distinct objects is always, from different threads, is always safe, no matter what those threads are doing, as long as, of course, they're operating on the object and nothing else, and no matter what the type is. So in particular, writing into an array of bools or array of chars on two different threads is thread safe as long as you're not writing into the same element. And yes, on x86, this restricts the code generation of the compiler. And yes, there may be a performance cost. Yes?
I assume what you're saying there is, even if they overlap in adjacent bytes in a D word or something like that, they're still going to be safe?
Okay, so basically the question boils down to why would you have anything else in the first place? The reason, like, why, who gave you the idea that two different addresses may not be safe in the first place? The reason is hardware operates in words. Like on x86, the 4-byte word is your native word size. And one of the ways to write a single byte on x86 is to do a masked write, which is you read the entire 4-byte word, you change the byte that you wanted to change, and you write the entire 4-byte word back in. And hardware, that's an option in hardware to do that. Obviously, you are restoring the value of the remaining 3 bytes to whatever it was before you started. If somebody else came in and changed one of the other bytes in that 4-byte word, you're going to blast it away and return it to what it was. So you're going to undo somebody else's write. Not in your own byte, but so bytes 0 and 1. Let's say this is byte. I'm writing 0 in here. What I'm really doing is reading the 4 bytes, doing the bitwise AND to set my byte to 0, and writing 4 bytes back. C++11 says no, you cannot do that during the code gen. Emit some other instructions that don't do that. So on some hardware, including x86, actually doing that masked write was the way everybody done it was actually the fastest way to do it, because the processor is faster operating on native word size. Accessing single byte not aligned on a 4-byte boundary was a little slower. And C++11 said, no, you cannot use the hardware instruction that actually writes a single byte at a given address. This guarantee only goes up to bytes. Accessing different bits in the same byte, all bets are off. Even if you have instructions that can access bits in a byte, the language guarantees nothing. Now, hardware may give you additional guarantees. So on x86, there is a BTS instruction, test and set, for a single bit. You give it an offset in bits, and it sets a single bit. You can put a log prefix on it, which would make it atomic. Hardware, in that case, guarantees you that writing into 2 adjacent bits with the log prefix is thread safe. But that comes from the hardware. Language doesn't expose it, and short of writing assembly, there is nothing you can do to actually get at that guarantee. And writing assembly, of course, you're out of the language, you're on your own. So, okay. Well, from the sun comes the sunburn, and from threads come the data races. Everything has its price. So the standard does define what is safe and unsafe memory access, and it says that concurrent accesses to different memory locations, and by that I mean different variables, basically, different addresses, are always safe, regardless of the type and what you do. Concurrent accesses to the same memory location are safe only if all accesses are reads. You don't change the value. If at least one thread changes the value, then concurrent accesses, both reads and writes, are undefined behavior. So if there is one writer and many readers, everybody is undefined, not just the readers or the writer. Everybody is undefined. Question? To avoid this problem, you must use synchronization. What kind of synchronization? Well, we've seen mutexes. There are atomics. There are the semaphores. you must do something to ensure that only one thread at a time is actually writing. Well, from data races came the logs, so we've already seen the logs. This plus plus is a modifying operation. You try to do it without the logs, what's going to happen? Well, undefined behavior, anything can happen. If you actually just try to do it in hardware straight up and assuming compiler doesn't take advantage of undefined behavior like I've talked about on Monday, what's probably going to happen is both threads will read the value of 0, they'll both increment it on the register to 1, and both write it back as 1, and it'll end up being 1. That's probably what's going to happen. Again, undefined behavior, anything you can end up with 4. All right. There is a slight question. Okay, what about the mutex itself? Both threads are accessing the mutex variable at the same time, and you have to assume that the lock member function isn't just a read. So how is that safe? Well, magic. Mutexes are special. I'll talk about magic in the second half. Mutexes are special. Okay, so back to our thing, how did it work? We had our pthread lock and unlock. Well, POSIX required that you couldn't do this reordering. That was POSIX stuff. All right. So how do we have it? What do we do now? Now it's that same thing has been ported into C++ memory model. In C++ memory model, it basically, well, you could say that it recognizes the lock and unlock, except of course in reality, if this is a separate compilation, it doesn't know what's in that function, so it has to assume that there might be lock and unlock in there. Therefore, it cannot reorder anything across a function that it can't see into. So the compiler is restricted to the worst possible case. Whatever it cannot prove, it has to assume that it happened. Yeah?
So then should those functions be in the same translation unit and it realizes it's not doing any mutex function?
Well, they are in the library, so here this is not an option.
Well, I suppose the case of, if those just normal...
Well, if everything was in the translation unit and you put stud... Oh, okay, so is your question what happens if they don't lock or what happens if they do lock?
What if they're not locking?
Okay, if they were inlined, or you had a compiler that is capable of doing whole program optimizations, the compiler could figure out that they're not locking and hoist them the normal way. If the compiler can see std_mutex, or whatever std_mutex actually unravels to, like the thing inside std_mutex that actually notifies the compiler to pay attention. And I'll show you what the thing is in the second half. But basically, if the compiler could see into this or into the std_mutex, it would notice there is a special mark there saying that this is the place through which you cannot move instructions. So if the compiler can see that, it knows exactly where that is. If the compiler cannot see it, it has to assume that it's there, the usual case. So the locks actually do work, and pretty much the way you expect. One thread locks the lock, enters what's called critical section. That's the part that requires exclusive access. The other thread tries to lock the lock, has to wait until the first thread unlocks. Then it enters the critical section, which requires exclusive access. They can both modify the shared data during the time they're in critical section. Then it unlocks and it can't touch the shared data anymore. Because accesses to the shared data, except reads, are undefined behavior unless you're doing them exclusively. That's actually not the... that's important. These guarantees are important. The other part of it is there are both correctness and efficiency guarantees. So what guarantees do you have, and therefore what can be optimized without violating the guarantees that you have? That's also important. So what do we have? What's the memory model consists of? The guarantees on the order of memory operations, reads and writes. Synchronization events, at which points the memory access is synchronized. What's called consistency model. I have two threads running on two CPUs. They're both scanning the memory and reading the data out of memory and reporting me on what they saw. Do I have the guarantee that they see the same state of memory? And if not, what could be the differences? if one of them is modifying the memory, what does the other thread see? What guarantees do I have about what the other thread sees? When does it become visible? So all of this is included in the memory model. So as I said, hardware has a memory model, language provides memory model, compiler provides memory model. The memory model is important not just for the hardware, but also compiler itself has to avoid making transformations that would violate the guarantees of the memory model. So hardware, obviously, if you have lock and unlock, there is something special going on in hardware that forbids shared access to the critical section. But the compiler has to obey that restriction too. The compiler cannot move the code outside of the critical section. So both hardware and the compiler participate in providing you these guarantees. So memory model is a property of the entire system, and any one component could give additional guarantees. All right, let's see what kind of guarantees we're talking about. Actually, on the hardware level, there's lots of things. We can talk about it from the point of view of what can be reordered. 2 reads, can they be reordered? Well, yes, maybe. Depends on the hardware. A read and a write, which means if I first read a value and then I write into a value, am I guaranteed that the read will see what was before and not what was written? Possibly. Write, read, same thing. Am I guaranteed to see the value that was written? 2 writes. Again, if somebody else is observing, can they see the second value before the first one? Here's a good one, dependent read. If you have int star p, and you want to read from star p, but you need the read of value of the pointer itself, can you reorder those? Can you first read the star p and then read p? There was a piece of hardware that did that. Anybody knows what that was? Dec alpha. Dec alpha. Dec alpha could reorder, if it could prove that the value of the pointer hasn't changed, it could keep the old value and swap the redundant read of the pointer with the referencing the pointer. Here is a good one. If you write into memory and you're reading instructions from memory, can that be reordered? If it can, you can't write self-modifying code. Not that you should. x86, our favorite platform, actually has a very strict memory model, almost total ordering. Write-read is the only one that can be reordered. Write-read can become read-write. And everything else has to be executed in program order. And by program order, I don't necessarily mean what you wrote, what the compiler wrote. The compiler can still reorder stuff all around. What the compiler wrote is the program order, and the hardware will execute it in that order, except hardware itself can swap the write-read, but not read-write. So if you have write-read, it can become read-write, not the other way around. Compiler, of course, can do any sort of reordering at once.
Question
Yeah.
about the reordering. If it swaps can it swap a write-read within a single thread, or do the write and read happen in different threads?
If it swapped it within the single thread, how would you know? You have to have an observer, because you'll see it a little bit later when I talk about it from the point of view of what's called memory visibility. But all of this makes sense if there is a way for you to observe it. So you would need either that same thread would need to observe, in which case it's not just these 2, there is another read stuck in there somewhere, or some other thread observes. So you need somebody to observe it. For just one thread with just these 2, well, okay, so within one thread, I mean, they'll have to execute in this order. So basically, like this, okay, so this read will always see the
Because you're generally talking about swapping orders when it happens and when they happen.
within on x86 within one thread, this read will see whatever you wrote. So in this sense, it cannot be reordered. ARM reorders pretty much everything by default. The only thing that it doesn't do is it doesn't reorder the data dependencies are respected on ARM. Okay, so, and this actually touches on this question that was asked. A better way to speak about this ordering is not so much about which operations are reordered, but what guarantees do you have on the visibility of memory operations. That's a more accurate way to talk about it. It's convenient to talk about it in terms of reordering reads and writes, because it's a kind of simpler model. But the more precise one is talking about visibility. So instead of saying which memory operations can be reordered, let's say how the effects of these operations can be observed in different orders. So we can now say that no, write-read cannot be reordered. Write-read is write-read. But the effect of the write may be able to maybe become visible after the effect of the read. And then that's what it means. So before we used to say write and read can be reordered. We will now say that the results of the write become visible after the read. So it's equivalent languages, but the visibility language is more precise. And it boils down to, in the end, what are the consistency guarantees? Because the visibility guarantees gives you, in the end, multiple threads observe the same memory and can see it in inconsistent state. One thread believes that these are the bits in the memory, and the other thread believes that something else are the bits in the memory at the same time. What guarantees, what can and cannot be different when viewed this way, and what inconsistency is permitted? That's basically this view-centric view of memory model. For the most practical purposes, all of this is equivalent, and it's just a matter of which language and mental model is easier for you to have. Okay, so before we break, I'm going to put this one statement, and then we'll go actually into the next part of it, which is, okay, memory model, schmodel, whatever. Locks work somehow. Who cares? And with that idea, I'll leave you here for the break, take time for questions, and then in the second half, when we come back, I'll explain to you what else is there other than locks, and why you care about memory model as a programmer besides the belief in magic. So one reason would be you don't believe in magic, you want to know how it actually works. But the other reason would be, as a programmer, you can take explicit control of all of these things that I told you about, which constitutes memory model. You can basically go in and directly ask memory model to like, please give me these guarantees, or please do not impose these guarantees on me. Yes, but that's obviously how you do it, specifically through the memory order argument, which you can only put on atomics. Well, you can also put it on fence, but fence is actually atomic fence. So yes, exactly. The second half will cover atomics, parallel STL, and coroutines.
When you talk about the write-read order and that it can pretend that the write has finished, is that talking in terms of the pipeline of the CPU itself and like how it makes its way through the cache layers and whatnot, and can just assumes that the write will finish and just reads as if it had been written already? Okay.
In terms of memory model itself, it's not that specific. So the question was basically, is the fact that write and read can be reordered, is it related to pipelines? And so the memory model itself isn't that specific. It doesn't tell you how it's arranged. It only tells you what's guaranteed. So if you want to know how it's arranged, it's specifically on x86. It mostly has to do with the write buffers, because the writes don't go straight into memory, they go into write buffers. And the reason they go into write buffers is, well, one of the reasons, I don't know, they're probably a pure hardware reason for speed, but one big reason is speculative execution. Because if you have to unroll speculative execution, you cannot have changed the state of the memory, because that cannot be undone. So if you have writes in a speculatively executed branch, where do the results go? They're held in write buffers until speculative execution becomes real execution, or you know that you mispredicted and you have to flush the pipeline. So those write buffers are basically asynchronous parallel channel for holding the results of the writes, while reads are being executed directly from cache. So you're reading from cache, but the results of the writes are sitting in the write buffers until speculative execution context clears. So that's one example. Yes?
But during for that thread that's going through speculative execution, if it's reading from a location that matches that write buffer, the data would come back from that write buffer.
For that thread, yes. But for any other thread that runs on a different core, no.
Yeah, because it's not global state yet.
It's not global state, that's correct. Yes?
Yeah, we have this example with the character buffer or character error. Just assume I have got a function and the compiler can't prove that it's not used in parallel.
Compiler assumes that everything is used in parallel
Okay,
contexts.
so the compiler, even if I write a program that never uses thread, the compiler has to
well,
use the slow code.
If you have only main, and basically from the main it sees everything is inlined into main, can it still? In theory, it could.
If I write a library with a function, it has to obey.
It has to obey, yes.
Okay.
Because remember, the binary, you're shipping .o,
Yeah.
so the binary code has been generated. In practice, they just changed the code gen to use like movesbl and similar things, that's just what the code gen does. They don't like fork it.
So we get suboptimal.
I've measured it on recent CPUs and I couldn't see the difference. But like when C++11 was introduced, yes, I could see the difference on the hardware at the time. I've measured it like 2 years ago and I couldn't see any difference. Slide 10. Okay, let's go back to slide 10. You trying to win the calendar? Okay, slide 10, that's a lock.
Does it make sense to think that the lock is somewhere in memory? Is it making sense to say there's a proximity between the data and the lock?
Okay, lock is definitely in memory. Furthermore, lock is a shared variable, and I just told you not to access shared data without a lock. And here we are accessing a shared variable inside this lock without another lock. So we'll figure out how that happens in the second half. Proximity-wise, tricky question. Hold that thought, it will come up in the second half. There are arguments for both, and you have to have very accurate discernment to figure out, in your case, is it better to put them together or not? It has to do with, so if only one thread accesses them, if the other thread wasn't there, then of course, yes, cache locality. If the other thread does access the lock and is banging on it trying to get the lock while this thread is in the critical section doing the computation, that's where it becomes tricky. Maybe, the answer is maybe not, and I'll show you why.
Also weak pointers.
Sorry?
Also weak pointers. It's when you want to keep them separate.
Well, both shared pointers and weak pointers have interesting relation with concurrent data structures.
If you have long-living weak pointer objects that outlive your storage of your shared data, you want them stored separately.
Well, the pointer itself, you probably don't care. It's the control block is where the synchronization is.
Yes, but you want them allocated separately.
The control block,
Without make sure.
yeah, the control block, yes. The pointer itself, wherever. Yeah, the control block. Well, again, it depends on how many you have. If you have only one, then it doesn't matter. Then actually, you probably want it together. No, if you have only one, or if you use them all on the same thread. If you have two, but you use them both on the same thread, you probably do want them together. If you have a lot and they're on different threads, then I don't want to kind of jump too far ahead, but I mean you know what I'm getting at, and for everybody else who doesn't, you will see it in half an hour. Basically, the accesses to this and to this have different performance requirements between when multiple threads are accessing. And it may be better to keep them far apart. Yeah. Oh, okay. I'm told to wrap up now. I'll be available during the break, so you can ask questions just privately during the break, and then in half an hour we resume with atomics, then parallel STL, and then coroutines.